In this video, I will be going over exponential functions, but the application of exponential functions and some real world examples. So again, just remember, right, with exponential functions, we could either have a growth function or a decay function, where the growth is increasing versus how the decay would be decreasing. Some examples could be like population, right? There could be a growth or decline. The value of an investment, something over time. Like think about like technology, right? Think about your cell phone. Let's say if you were to buy your cell phone, right, and the original was, $999. Well, after having that cell phone for 5 years and you go to trade it in, is it still worth that $999? Well, no, it's lost value over those 5 years. So those are some examples. And oh, that's just another example. Then here is our formula, the function that we will be using for our exponential application for our exponential functions, where A is the final value. Here we have our initial value times we have our R, which is going to be our growth or decay rate, and T for time in years. And making sure that we go through and identify those pieces. So like in this first example, the population in the year 2000 was approximately 6.08 billion. So I could also write this as, since it's billion, I could write this as 6.08 times 10 to the ninth power. Now, notice it says the annual rate of increase, so keep in mind increase, was about 1.26%. So now when we're talking about trying to figure out in this first part, what is the growth rate? Well, here we're not going to use the percent, which was the 1.26%. We need to make sure to convert our percentages to a decimal. And remember, this is the same as out of 100 or dividing by 100, which is the same as just moving that decimal 2 places to the left. So here, our growth rate is that 0.0126. This is what you're going to use when you set up your function. That means the growth rate factor, because we are increasing, we are adding. Because remember, you could add to show growth or subtract to show the decay. And again, growth rate, growth factor. So here we have 1 plus that rate here of 0.0126, which will be 1.0126. So now let's just say in part B, we're going to continue that same rate. And now let's write that function, modeling the world population over time. We don't know yet what T is, so we'll still use T in our function. So A, the final amount, because we don't know what the final amount is, right? We're starting at that 6.8 billion. So this is our initial. So here we've got A is equal to our 6.08 billion, then times, remember now this was that growth factor or decay factor. In this case, it's growth. So 1.0126. Then, do we know what the T is yet? Our time in years? No. So I'll put T here, and that is our function. Now let's go to part C so that you can see how we're going to solve these. Now we're going to let T be the number of years past the year 2000, right? So if we're in the year 2023, that means what is our T? Our T is going to be 23 because now we're in the year 2023. Now we can estimate the population now. So A is equal to, right, because we're looking for the final. So the original again was, sorry about that, was 6.08 times 10 to the ninth times that factor of 1.0126, but now raise that to the 23rd power. Then putting that in the calculator, you're going to get that the population would be approximately, final population, 8.109 approximately, I just rounded here, times 10 to the 9th power. So that's the approximate amount of people. So go ahead and pause the video and try this try on your own. And here we go. Notice how you are investing $75,000. So that's the initial investment in a 30-year CD that grows at a rate of 12.5%. First off, growing. So I'm going to add at a rate of 12.5%. So remember, we're not going to use 12.5%, right? That's out of 100, divide by 100, move that decimal 2 places here. So we have that rate of 0.125. What will the value of your investment be? So we're looking for the final amount after 30 years. So there is our time. So there's your T. So now we set this up. A is equal to 75,000 because that was the initial times 1 plus, because we're growing, at 0.125. Raise that though to the 30th power because that's your time in years. Then remember here, when you're writing your answer, make sure that it makes sense. Because if I'm talking about money, that means we need to round to the nearest cent. So the amount, the final investment, or the value of the investment, you should get $2,568,247 and approximately 87 cents. So that is the final investment. Now let's take a look at example 2. The bear population in Yellowstone has been decreasing at a rate of 2% per year. So now notice, if this is decreasing, we're going to have decay. Now we're going to subtract to get that growth or decay factor at a rate of 2% per year. So again, 2%, right? We're not going to use 2 because that's out of 100. Move the decimal 2 times to the left. So this is 0.02. That is our rate. This year, 1,573 bears have been identified. So here is our initial value. Now we're going to write a function that models the bear population over time. So again, we don't know what time is yet, so we'll still use t in our function. A is equal to the initial, which is 1,573 times 1, but now minus, right? Because we are decreasing by our rate of 0.02, right, to represent that 2% to the t power over time. Now, let's assume we're continuing with that same decay rate. How many bears will there be in the park and in 10 years? So now there's your value of t. So A is equal to 1,573, right? Well, then let's set this up. Well, 1 minus 0.02. That's now going to be 0.98. Now raise that to the 10th power. Then again, make sure that your answer makes sense. So if I'm talking about the number of bears, could you have a decimal or part of a bear? Well, no. So the final amount of bears that remain in the park is going to be approximately 1,285 bears. So go ahead and pause the video and try this try on your own. And here we go. Cars depreciate in value. So depreciate, meaning it's losing value, going down, which means we're again going to subtract. In the value of the moment you drive the car off the lot at a rate of 20% per year. So again, 20%, right, is not what we're going to use for our rate. So here our rate is out of 100, or move that decimal, so 0.2. You pay $45,000, so that's the initial amount for a new 4Runner. What will the value of your car be after 4 years? So there's your time. So here we go. A is equal to, because we're looking for the final value, right, after 4 years. The initial, what you spent, was $45,000 times 1 minus, right, that rate here, so 0.2, not 20, and raised to the 4th power. So now here, when you solve and simplify this function, you end up with that value after 4 years will be $18,432. Now we have one other type of exponential function. What if interest is compounded? So you could have what's called compound interest, and this could occur more than once per year. So notice how all the other previous problems we were talking about was just per year. But what if it's compounded more than once? So here, notice there's a little difference in our function that we're going to be using. Notice how we have this n value here. N now is going to represent, because everything else is the same, but n is going to represent how often the interest is compounded in the year. So each of these represent different values, right? Well, annually, like your birthday is annual, so it only happens one time per year. So semi-annually means n is going to equal 2. Monthly, well, how many months are in the year? 12. Weekly, how many weeks are in the year? 52. Daily, how many days are in the year? 365. So these are the values here if you are compounding that amount per year. In example 3, your parents deposit $5,000. So they put in, that is the initial amount, into a college fund that pays 7.2% interest. So again, same thing, right? We're not going to use 7.2% because that's out of 100. So again, divide by 100, move the decimal, right? 2 times to the left. So that rate is 0.072. And compounded monthly, which means n is equal to 12 because there are 12 months in the year. We're going to find the account balance, so the final amount, right? So we're looking for the final after 5 years. So there's our T. Now, keep in mind, we don't just have the rate now, it's the rate divided by the amount that the interest is compounded, and we're multiplying that same value by our time in years. So the final amount, A, is equal to the initial, which was deposited, $5,000, times we're compounding, so 1 plus our interest rate, so 0.072, but divide that now by 12 because that is that n value here. Then here again to the 5 because that is your T, but we also need to multiply that by the amount of times compounded, which is monthly, or 12. So now this is what we are calculating here in our function. So the final deposit is, and again, make sure that it makes sense here when you write your answer, right? So if we're doing money, you need to round to the nearest cent. So the approximate final value would be $7,158.94. So go ahead and pause the video and try this. You try on your own. And here we go. Notice how when you read through this, there are 2 options. So I'm going to set this up as option 1 and option 2. So in option 1, you have the initial amount, right? Because the parents are given that gift of $20,000. So option 1 has $20,000. That's the initial amount. And they can choose here between the 2 options. So here we go. So you invest that gift at an annual rate of 8%. But remember, you should have moved that. So it's now 0.08. Compounded semi-annually, which means n is equal to 2. Then option 2 is to invest this same gift, so it still stays at $20,000, the initial amount. But now the rate you should have noticed was 7.75%, or remember, right? Move that decimal, so 0.0775. Compounded weekly now. So n's not equal to 2, n is equal to weekly, which is 52. Then assuming each investment has a term of 18 years. So they both have that time of 18 or 18 years. Which is going to be the better option? Which should they choose? So that means now you have to do this problem or use this function for compounding not once but twice. So A is equal to 20,000 times 1 plus, right? Because we're compounding 0.08, but you should have divided by 2. And again, raised to the not only just 18 power, right? Because here with our compound, don't forget to also multiply that value of n, which was 2. When you put that in the calculator, you should get, and again, we're rounding because we're dealing with money, $82,078.65. Now, option 2, you should have set it up as A is equal to 20,000 times 1 plus 0.0775, but now divide that by 52. Raise again to the time in years 18, but multiply that value also by 52. So once you put that in the calculator, you should have gotten approximately $80,000, $80,615.73. So notice how the option that the parents should have gone with is option 1. Now go ahead and pause the video and try this last you try all 3 parts on your own. Now let's see how you did here. Notice how for all of the functions, you had to write the function and find the value of each function after 5 years. So we are using P for 5 years. So a 12,500 car depreciates 9% each year. So you have the initial amount depreciate, so you should have subtracted 9% or 0.09. So here the function you should have set up is A is equal to $12,500 times 1 minus 0.09. Raise that to the 5th power because we're using P for, we're using 5 years for our T. You end up with the final value of the car, $7,800.40. Then the baseball card you bought for $50. So there's your initial, increasing at 3%, increasing, so adding 3% rate, so 0.03. Again, you should have set this up. A is equal to $50 the initial, then 1 plus 0.03, and again, raise that to the 5th power for your time. And the approximate value of the card is $57.96. Last one, here you have that initial, so $8,000 is the initial, growing at a rate of 3.25% or 0.0325, but compounded monthly. That means N is equal to 12. You should have set this up as A is equal to $8,000 times 1 plus, because of the compound, 0.0325 divided by 12, raise that to the 5th power. But remember, right, also multiply by that value, that N here, compounding monthly. And you should have gotten approximately $9,409.52.